Hello student, welcome to our first lesson in this topic, and in this lesson we are going to look at stability of isotopes of elements. We start with the introduction. Now in book 2, if you can recall, we studied the structure of an atom, and in the structure of an atom we have nucleus, and inside the nucleus we have protons and the neutrons. Then we also have the energy levels, or what we call the shells, and in the energy levels we have what we call electrons. Now in form 2 we also studied the reactions involving the valency electrons. But when we come to this topic, we are going to look at reactions that are originating from the nucleus. And remember, in the nucleus we have what? We have protons and the neutrons. So we are not referring to the electrons that are in the energy level. So these reactions that are originating from the nucleus, we call them nuclear reactions. Then from there we can look at the stability of isotopes of elements. We start with an atom, the composition of an atom. We say that atom consists of tiny nucleus, and inside that nucleus we have protons and neutrons and energy levels, and in the energy levels we have electrons. Now when we talk of nuclei, we are referring to all atoms of the same element, whether those atoms have the same mass number, or they have the same proton or atomic number, or they differ in protons and neutrons number. All atoms of the same element, we call them nuclides. Now these nuclides are represented by their atomic number and mass number. For instance, we have chlorine. The chlorine here, this one is chlorine 35 and this one is chlorine 37. The two are referring to the same element, chlorine, but they have different composition, and therefore they represent different atoms. Therefore these are nuclides of chlorine. When we come to isotopes, we are referring to atoms of the same element with the same atomic number and a different mass number. And just a reminder, when we talk of atomic number, we are referring to the number of protons in an atom. But when we talk of mass number, we are referring to the sum of protons and the neutrons. So we are saying isotopes are those that have the same atomic number or the proton number, but a different mass number. For instance, we have uranium 235 and uranium 238. These are isotopes of uranium. From these two definitions of nuclide and isotopes, then we can say that all isotopes are nuclides, because they are referring to atoms of the same element. But not all nuclides are isotopes. Remember, nuclides can have the same mass number, the same atomic number, but when we talk of isotopes, we are saying that they have the same atomic number but different mass number. We also know that some isotopes are more abundant than others. In other words, they have a higher percent in the naturally occurring atom. For instance, we have chlorine 35, which is more abundant than chlorine 37. This chlorine 35 represents 75%, while chlorine 37, it only occupies, or it only represents 25% of naturally occurring chlorine. Then we move to nuclear stability. We have seen that in our atom we have nucleus, and inside that nucleus it has protons and neutrons. And in this element, the first 20 elements, the number of protons and neutrons are always the same. Actually, if you take an example of calcium 20 or sodium, you will find that the number of protons and the number of neutrons are the same. Now when we take that ratio, proton is to neutron, it is supposed to be 1:1. And when that happens, then we say that that nuclide is stable. For example, we have calcium, which has 20 neutrons and 20 protons. And therefore, the neutron is to proton ratio is 1:1. Therefore, calcium is stable. But as the atomic number of element or atomic number of element increases, you will find that that ratio also increases. And as the ratio increases, you'll find that they will deviate from that stability and they will become unstable. But that ratio can go up to 6:1. But when it is around 6:1, this ratio also falls within the stability region, as we are going to see in our diagram in the next slide. Now, as atoms get heavier, there is a marked deviation from this ratio, that is neutron is to proton ratio, where we have that the number of neutrons increases and supersedes that of protons. And when that happens, then the nucleus is likely to be unstable. And when you have unstable nuclide, it has to undergo some changes. It has to split. It has to disintegrate. And when it disintegrates, it emits radiation. And those radiations are in form of particles. And when it emits those radiations, then a new product is formed, or a new nuclide is formed. And this new nuclide has a completely different composition. The stability of nuclides can be illustrated by plotting a graph of number of neutrons against the number of protons for the various nucleus, as shown in our diagram here. We have that on the x-axis we have the number of protons, on the y-axis we have the number of neutrons. So we are plotting number of neutrons against the number of protons. You can see that for those elements that are light, that is the first 20 elements, they all lie within this straight line, and therefore they are stable because the ratio of neutron is to proton is 1. Therefore they are stable. They are not radioactive. But as the atomic number increases, as you can see in this region Y and the region X, this ratio is not the same. It is not equal to 1. In other words, we are saying that number of neutrons is not equal to the number of protons in region X and region Y. But we have said that previously, if the ratio is around 6:1, it still lies within the stable region. And that is why we are saying all stable isotopes lie within the shaded region. So it means that this shaded part, it contains stable nuclides. So let us look at what the graph contains. You have seen where we have X and where we have Y in our graph. So we have straight line. All the nuclides falling along this line are non-radioactive. In other words, their ratio is 1. That is, neutron is to proton is equals to 1, and therefore they are stable. Note that these nuclides, they are the first 20 elements. They are lighter. They are nuclides up to 20 protons, and therefore they fall within this line and they are stable. But when we come to the shaded region, this shaded region forms what we call the band of stability. The nuclides that lie within this region are still stable. Although the ratio is not 1:1, they still lie within the stability region. And we have seen in our previous part that all stable isotopes, they lie within the shaded region in our graph. So any nuclide that is not lying within the shaded region, like in the position X and Y we have seen in our graph, they undergo decay, or in other words, they are radioactive substances, and they have to disintegrate. And as they disintegrate, we say that they are undergoing decay, and they disintegrate until they form a stable nuclide. And that decay, it forms a new nuclide, and the particles, there is emission of particles. We are going to see later the particles that are emitted. So in region X, that is situated to the left of our bud, that is the upper part. In this region, the neutrons are too many than the protons, and therefore the ratio of neutron is to proton is greater than 1. Therefore, that region contains of unstable nuclides, and therefore those unstable nuclides have to undergo what we call radioactive decay until they acquire stability. When you come to the region Y, which is again on the right side of our stability line, this again, it means that they have many protons than neutrons, and therefore the ratio neutron is to proton is less than 1. It again implies that the region constitutes of unstable nuclides. So it implies that the nuclides that are in region X and in region Y, they have to undergo decay so that they can acquire stability. Then from there we can move to radioactivity. This is a process where an unstable nuclide breaks up. It breaks up to yield another nuclide of different composition with emission of particles and energy. We can also say that it is the spontaneous disintegration. There is breakdown of that element until, or that nuclide, until it acquires stability. And stability will be achieved when the number of neutrons will be equal to the number of protons. So that process where this unstable nuclide breaks up to yield another nuclide of different composition with emission of particles in energy is what we call radioactivity. Now, those substances that undergo radioactivity, we call them radioactive. And isotopes which are radioactive, we call them radioisotopes. So note that isotopes, we defined it later. If these isotopes undergo radioactivity or undergo radioactive decay, then we call them radioisotopes. So radioactive decay is a spontaneous disintegration of radioactive nuclides. When we talk of spontaneous, this is splitting that is occurring by chance. You cannot predict which nuclide will disintegrate next or will break next. This one is governed by chance, and therefore it is spontaneous disintegration of radioactive nuclides. Now, radioactivity is a nuclear process. Remember, we have said that in book 2 we learned about chemical reaction, and these chemical reactions occurs or they involve what we call the valency electrons. But when we talk of nuclear process, it involves the nucleus, or the reaction is originating from the nucleus, and in the nucleus we have protons and neutrons. Then we can look at differences between chemical and nuclear reaction, and we have the table here. In the nuclear reaction, this one takes place within the nucleus, and it involves neutrons and protons. But when we come to chemical reaction, it takes place on the outer energy level that contains the valency electrons. Then number 2, the nuclear reaction releases large amount of heat energy. But when we come to chemical reaction, the heat energy released is negligible. It is much less. Then number 3, we have that in nuclear reaction, it's not affected by environmental factors such as temperature. But when we come to chemical reactions, these reactions are affected by environmental factors such as temperature and pressure. So those are the 3 differences between chemical reaction and nuclear reaction. Just to remind you that nuclear reaction is originating from the nucleus, while chemical reaction is occurring due to the presence of the valency electrons that are on the energy levels. So then we move to assignment. In this assignment, it's just testing what we have just learned. So make sure that you revise. If you can't attempt, it's always good to go and revisit the video. Make sure that you comprehend every concept and then come and attempt the assignment. So thank you, and let us meet in our next lesson.